Yeah, thanks for the introduction and for the opportunity for me to give a talk here today. And thanks a lot in particular to the organizers, including you, Sasha, for making this extremely nice program happening. I'm enjoying that very much. I think it's a great place and a great opportunity for people to come together. What I'll be reporting on today is on effective wave fields, and there's a bit of sort of an ongoing story behind it, which I will try to tell quite a bit about. Not everything though, because then I think I would need the 1.5 hours or even more. It's sort of outlined in a bit of a storytelling way, at least to some degree. So I'll get to that. And also, what I certainly want to mention is my two collaborators, Luke, who you all know very well, who's traveling today, but will be back this week, from Adelaide, and also our joint PhD student, Sebastian Ruprecht, who's just handed in his thesis about a month ago, and it's planned that he will defend his thesis just before Christmas. So quite, well, if not almost all of the results I'm presenting are actually obtained by him. Or at least he's involved in a very strong way. Okay, so what's the outline? What do I want to tell you? Well, we've been interested in sea ice and in wave interactions with sea ice for a while. When I prepared this talk, I thought I should say I've been working on this for about 15 years, but it made me feel very, very old. And then well, anyway. But you'll see this. I'll talk a bit about the motivation, how we came to this problem that I'll be talking about, and then I will drift away from it more and more, because what actually happened is that we started with this problem. We simplified and we tried a few things and we got a few results, which then puzzled us to some degree, and so we simplified even further to understand the mechanisms and what's going on really, and basically in the end I think we understood quite a bit, which also then relates back to the more complicated problem, and I think this is where we quite haven't finished yet, and where maybe after the talk we can discuss about a little bit about what you think about this. Okay, well let's start. So where's the start of the story? Start of the story is the following. We've been interested in computing, well, basically scattering. That's the thing that we've always looked at by a medium like this, right? In particular, for quite a while ago, we've really looked into different, sometimes quite sophisticated methods to compute scattering characteristics of such a medium involving many scatterers, and doing that in a computationally efficient way. Basically in all those models, what we have is we have these bodies here, which we model as thin elastic plates floating, and what we do is we have an incident wave which is about the same size and wavelength as the scatterers, and yeah, what we want to do is we want to be able to compute efficiently what happens when incoming waves are scattered. I mean, you're all very well familiar with this problem, so maybe I don't need to say much more. But the point being that in all those things that we looked at before, it was always deterministic in the sense that we said there are all these ice flows here, could be very many, and we want to know what happens to an incident wave. And so then, not so long ago, maybe 5 years ago or so, we started thinking about the fact that actually what's going on here is these are arranged sort of in a more or less random way. I mean, that's not quite true because there is some sort of characteristic space between them and that sort of stuff, but it's really more of a random medium in the sense that this is maybe thought of as a realization of a random medium. And then we realized that there are quite sophisticated methods in physics and mathematics to compute scattering characteristics of random media, and we're hoping to use these ideas to get some handle on these problems here. Okay, so basically,
Can I
be,
ask something?
yes, sure.
Is it okay to ask?
Oh, you
Yeah,
go for it.
or if you just go back to the previous panel, so basically, I mean, you know, there's this little curve, you know, like a tail kind of, you know, you see that blue curve?
This one here, yeah.
Is that sort of, you know, you think
Just
of that
like
as a
a
wave
wave
path? Is
Yeah.
that what you think?
No, it's a wave coming in.
Yeah, it's a wave coming in.
I see,
That was the idea. Yeah, this is just a bit of a sketch.
Yeah, okay.
Yeah, but you're right. Basically, what this is supposed to mean is here you have the basically continuous ice sheet of sort of random, or more or less random looking thickness, and then when you go out towards the edge of the marginal ice zone, you get all these broken up bits which become smaller and smaller, and out here you basically have the open ocean.
Right.
That's just a sketch of
Yeah,
the
okay.
situation. Yes. Okay. So if to be a bit more specific, maybe let's look at this problem where you here you take a cut through the Arctic Basin. Just look at here is a 1,000-mile transect, and this was as far as I know obtained from upward pointing sonar. And what you see is that you've got this something that looks like a typical realization of a random process in terms of this thickness profile. If you zoom in a bit further, then this is typically what you see. You see all these keels and ridges and all that. And so what we thought maybe to start out with is to try to model and to come up with a way to understand wave propagation in this thing, thinking of this as one realization of a random medium. What has been done before, and I'll also get into that a bit more in a bit more detail soon, is basically you discretize this numerically and you compute what's the scattering characteristic for this one realization, which is sort of looking back at the one deterministic problem or deterministic profile that you might have obtained from measurements. And there's a simple and effective solution method, the step approximation. I'll get to that in a few slides, but the point being that basically you take one geometry, you discretize, and if you do it in a smart manner, you don't even need to do that in a sort of like one big matrix in the end, but you can use a recursive iterative algorithm, which is computationally very, very cheap. Okay, so that's fine. We can do that. And what you typically see, the output of such models, is that you see wave attenuation along these transects. And basically, a typical thing that you see is if you look at the log of the modulus of the wave elevation, and then you see pictures like this, or as functions over distance. So these different colors are for different incident waves. So these are for very long waves. So 35-second wave here is almost no attenuation over this distance. And then if you increase the frequency of the wave, so if you increase the frequency, you get stronger and stronger attenuation, and you see that this being because the log here, the exponential decay is more quickly, and all of these single ones, they look roughly linear, right? So on a log scale, they're linear, so it's basically exponential attenuation by scattering.
I want to just, well, because we've got people here that understand where you're going with this stuff, right? And you've got to understand the theory and all that. But this results that Vernon published was disproved by measurements, right? Mm-hmm. It's not, and I think because it's, one-dimensional, so the scattering is so long, each of those ridges now stretches from plus and minus infinity. That's going to create a much greater.
Oh yeah, no, I totally agree. I know you're
trying to understand it mathematically to explain this. Yeah.
Yes, yeah. No, actually, yeah. Maybe I try to explain that in the beginning, but maybe I should stress that much more. You're completely right about that. Is that basically what I'm doing here is I'm trying to reduce the problem so far that we can really get a handle on the mathematics on the one way. But on the other hand, also to really get see what physical mechanisms happen in those models, and then the interesting question, of course, is then go back and say, well, if we take this model, then we can do this, and we see these physical mechanisms going on in these models. But are these actually the ones that are really there? Of course, that's a very important question, right? And that's and I'll come to that towards the end as well. But you're completely right about that. Okay, and Yeah, so these are the typical pictures you see in these kind of simulations, and this basically this effect, if you like, is quite well known in other branches of physics, in particular in solid state physics. It's known as Anderson localization, and there's been have drawn a lot of attention in the well, up until now, but I guess starting in the 1950s. That comes from the question of how electrons propagate in materials and crystals, basically. But again, there as well, you see, if you look at this in the frequency domain, you see precisely this exponential decay in if you look at the scattering. Okay, so this is basically what we wanted to understand better, and what we did is now we looked at a thin elastic beam floating on water. So basically, what we have is we have a beam here floating on the surface, which now, because of these variations in the thickness and of the beam, has a what I would call varying rigidity and a varying mass in terms of non-dimensional parameters. And then for the water, we just look at rotation in visit theory, time harmonic waves. So basically, very standard. We have a no flux condition at the bottom, and what we're interested in is now a wave coming in from minus infinity and seeing what happens as the wave propagates. And I will show you what we got with this, but I also want to show you a little bit about the theory behind it and the mathematical algorithms we developed. And in order for those not being too technical, what I'll do for now is I remove the water. Right? This is I'll add the water back in a few slides, but just because the whole expressions are a lot shorter, a lot neater. The whole ideas can be understood, I think, a lot better if we remove the water, because it just complicates things in terms of technical details a lot. I just want to get rid of that, and then I explain how to add it back in. So just for a few slides, we just look at wave propagation in a thin elastic beam, basically with nothing around it. So then we have the beam equation here, as just on the previous slide. And as I said, we look at time harmonic waves. So we have a displacement, spatial displacement. We have factored out the time dependence. If we take the real part, we get the displacement. We have a frequency parameter. I said we look at this in a non-dimensional way. So with our frequency parameter here, basically just omega squared. We take a unit amplitude wave incident from the left, and the two quantities that determine our problem are the beam rigidity and the beam mass, given by these functions b and g. And what I'll show a little bit also in what follows is simplifying the problem a little more, is either taking the beam rigidity to be constant and just looking at variations in the mass, which what I'll refer to as the varying mass problem, or I switch them around. So I have a constant beam mass and just look at a varying rigidity. Or if I have both of them varying, which I think of as I have a varying thickness really, and that affects the beam rigidity and the beam mass, I have a varying thickness problem. Okay, so if I just look at the varying mass problem, things are reasonably simple. I can always compute my local wave number just by this quantity here, and now. So far, everything looked very deterministic. I have the function b and the function g given. And what I want to do now is incorporate this randomness, and I do this in the following way. I say, well, actually, my function g is something like in this context, a mean, some mean value, and some fluctuations about it. So basically, I take this. I say this is basically my mean mass, and then I say I add onto that epsilon, which sort of determines the strength of the randomness, if you like, times some random process, which is of order 1 and has mean 0. So some random fluctuations about this g bar of strength epsilon. Okay, if I look at the varying rigidity problem, I can basically do the same thing. Wave number computes in an analogous way, local wave number, and again for this rigidity function B, what I do is I say, well, it is actually a fluctuation about a mean rigidity, again, in exactly the same way. So fluctuations are of order 1, but I multiply them by epsilon to determine the strength, and then, of course, they have to have mean 0. Okay, so how does that look like? Well, if I now look at one realization of such a process, then basically the typical profile, say, of rigidity looks like this. So I have this mean, I have this mean B here, and then there's some fluctuations, and what I want to have, the way I've set up the problem in order to make it computable numerically towards minus infinity and plus infinity, eventually it goes to the mean value again. I'll talk about some analytical theory later on where we don't need that, but just to have a picture in mind, so there's a long piece where I have this random variation, and as I said, because I have epsilon times this process of order 1, the actual sort of characteristic amplitude is epsilon. Right? This is what it looks like.
A million ways, maybe even more, of choosing these random.
Oh yes, we can definitely talk about that later on.
But there must be some characteristic length scale.
Yes, I'll get to that.
Okay.
Yeah. Okay, so if I want to compute this numerically, I said I want to use a step approximation. So what I do is I approximate this continuous profile by steps, and basically this is what it looks like. Okay, this is for the numerical computations, just to have that picture in mind straight away as well. So I use m, and basically what I always do, I use m intervals. M has to be quite large, of course, of equal length. Okay. So what I do, just to give you a few details of the numerical method, what I do, well, basically now I look at one of one of these intervals where the wave number is constant, so one step, and I can say, well, if I have a beam in vacuum, where I can write the displacement basically as in terms of these 4 components, which is a propagating wave from left to right, an evanescent wave from left to right, and then a propagating wave right to left, and an evanescent wave right to left. Not more than that. There's just these 4 modes. That's the sort of the nice thing about the in vacuum beam. And you can already imagine if I have water underneath, this becomes much more complicated. But I have a lot more modes, and I have to be very careful. But basically, so here I just have the 4 modes. So that's why it's much easier to explain it for the simpler problem. Okay, then what I also have, I have a right-word traveling incident wave, just of the standard in the standard way. And basically, the way I set up the numerical method now is I say, well, in each of these steps, I have an expression like this with different coefficients. You see here the m denoting in which step I am, and of course I have the local wave number corresponding to that step. And now I have to couple them, and I do that by coupling them through these conditions here, where this double pointy bracket means it's the jump. So I have basically continuity of deflection, continuity of slope, continuity of bending moment, and continuity of shear stress. Right? And if I apply that at each step, then I get a system of equations that I can solve for.
Bending moment. It's a second derivative multiplied by rigidity.
Yes, there's a b. Yeah, you're right. There's a b missing there.
Oh yes.
Yes. Yeah. Sorry. You're right.
In third as well, right?
I think you have to be careful. It's the derivative of d times the second.
Okay.
Yes. Sorry. Yeah. I've been slightly negligible here. Yes, but you're completely right. Yes. Yeah. Thanks for that. There's actually a slightly nasty typo here. Okay, so what do I do? How do I do that? Well, I look at one step. I've just said, well, if I look at the waves incident on this step from the left, they have this form here, the propagating part and the evanescent part in terms of the local wave number Kn corresponding to here, and then on the right-hand part I have its incident on this step with the leftward traveling waves. But with local wave number Kn plus 1. Okay, and then basically I use the standard thing that you do when you set up a problem like this. You say, well, if I want to know what is reflected by the step on this side, or what travels this way, maybe that's probably better to say. Well, it's the reflection of this thing plus what is being transmitted from this piece here, and you can write that in this form. And then when you want to work out what goes the other way, well, in the same manner, it's the transmitted part of this stuff plus the reflected part of this, right? And you can write that in terms of the coefficient of the modes with these reflection and transmission matrices from left to right. Each of these is of course 2x2 matrices because we've got 2 modes. And then this can be written in this form down here in matrix form, and this is now a 4x4 matrix because each of these blocks are 2x2 matrices. Okay, and so this is very cheap numerically, and as I said, if you now set it up for all the steps, what you can do is actually do this in an iterative manner. I don't want to go into the details of that. There's actually I think, well, for a very similar problem in this CIS context, Luke published some stuff on it, I don't know, 5-6 years ago. Okay, so one thing that we should briefly talk about, I don't want to go into many details, is, okay, so one thing I did, which you might think is slightly nasty, I approximated my continuous profile, and I've been putting into this that it is continuous a lot of times. Actually, now numerically, I use the step approximation. Is that any good? Because steps cause scattering, right? So actually, you might think, well, by doing that, I had a lot more scattering interfaces, so things might screw up. So what we did is we looked at the step approximation for deterministic wave number variation, and we solved the problem in a completely different way by an integral equations approach using a Green's function. And there is actually, because it's a fourth order equation, there's a bit of fun how you can set it up. If you do it just for the displacement, or if you set it up as a mixed problem for displacement and velocity and so on, or for displacement. And well, anyway, I don't want to go into the details. Point being that, again, the deterministic solution then looks like this. You can solve for it using an integral equations approach. And I'll just show you some results to convince you that the step approximation does not cause any problems. So basically what we did is we looked at a profile which has a sort of a hump, we called it, sort of a fourth order polynomial as far as I remember, and of some height. And so for a large hump, small hump, here's the reflection coefficient as a function of hump length. And you see the results from the step approximation and from the integral equation, and you see that they're basically perfectly on top of each other as long as you use enough steps. But that kind of information, of course, we use then for the next simulation, so that we got some idea of how many steps we need, how fine we need the discretization. And you can see that here is again now as a function of hump amplitudes, and you see even for large amplitudes, this is for KL equal 4, the hump is slightly larger. Longer, then again everything works fine, right? You can do convergence studies on that. We did a bit of that just to learn.
So the step approximation gives you a sort of discrete length, right? And when you solve this integral equation, you also must have done it on some discrete length, right? Did you compare the convergence of the two?
We compared convergence. Yeah. One thing, one thing that is quite interesting, now that you ask, is the question. One important question is, which quantity are you interested in? If you look at displacements, the convergence behavior has the tendency to be quite different compared to if you look, for instance, in terms of reflection coefficient. That's one thing to be slightly careful about. And the other thing that is quite interesting is if you do the integral equations approach, you have some choice of which conditions you impose in a natural way, and which you impose in an essential way, right? In the way you set up the system of equations. And again, that also has quite an influence on the convergence, depending on which quantity you're actually interested in. So you got to be slightly careful in what you're doing there. Okay, what I just want you to take from the slide is we know what we're doing with the step approximation. Okay, so now that we can do it for one profile, of course, what we're interested in is this effective wave field. So basically, the question is, if we look, and these are the two quantities I'll be talking about a lot in the rest of the talk, is the individual wave field, which means I have my random process, I take one realization of the process, then I have a variation of rigidity or mass or thickness, whatever I had, and I compute the wave field. That's what I call individual wave field. Okay. What I can also do is I take one realization of the process, I compute the wave field, I sort of put that to one side, save it. I take another realization of the process, compute it, put it aside. Do that for a lot of things. Typically, what I'm showing you is I do these draw and compute 1,500 times, and then I have all these wave fields for the different realizations of, say, thickness profile, and I compute the mean wave field, right? I just take the average. And that is also some quantity, which is a wave field, but it's sort of the average of all those wave fields. Okay, and if I do that, this unfortunately, it's not, the contrast isn't very good. But here are just a couple of examples to sort of show you that one has to be very careful of what's going on. What I've plotted here is, so each of these plots is supposed to have two curves. One is a gray one, which is this very highly oscillating one, which is a typical individual wave field. And it has a second curve, a darker one, basically a black one. You can see here as this pretty constant curve, which is the corresponding effective wave field. Okay, and these are, so they both things, both plots show basically the same type of curves, except that here I've chosen a thickness profile, which is more random. I'll quantify that in a second. Whereas this has a smoother profile. Okay, but what one sees here is that in this setting here, which is actually I guess it's not giving away too much here by telling you that this is in a regime where the wavelength is roughly of the same length as the variations. So so this is what you see here, and you see that basically there is some attenuation of the wave going on, right? The envelope sort of becomes narrower. There's attenuation of the wave, but basically in the mean wave field you don't see very much here, right? But you can sort of guess if you look very closely that there is some attenuation. I'm sorry, I should have made these plots a bit bigger. There was more space on the slide, right? But you can see that here it starts at 0, and here it's sort of below 0. But it looks very different here, where again you have these random looking fluctuations in the individual wave field, but you have this very strong decay, and this is again a log scale, so linear decay on a log scale, so exponential attenuation of the effective wave field. But what is also important to note, and this is one thing to realize, is that here you sort of, I guess, without knowing more at the moment, there might be some relation between these, but for this curve looks completely different from this, right? So one has to be very careful with this effective wave field here.
But what's the reason why they're so different?
I'll explain that. That's actually one of the key points of my talk. But just to give you some more insight on what goes on, because I was just saying that those profiles are different. As I said, this here is for a randomness profile. Let's put it this way, or for randomness profiles where the fluctuations are roughly of the same length as the incident wave. And so for this particular case, it looks like this. For this one here, I have much smoother variations on a longer scale. So this is the plot where the typical realization of thickness profile looks like this. Okay, so this seems to have a large influence, right? In particular, in which way these wave fields are related. Yes.
Sorry, it's just one frequency that you are. It's one monochromatic.
Yes, right. It's one monochromatic
It's
wave.
the same in all
Yes.
experiments. You're just varying the length scale.
Yes. Sometimes I'll get to that. Sometimes I have plots over wave number or plots over frequency, but here it's really just one particular one. Okay. So yeah, just to give you the precise formula. So these attenuations, I can compute attenuation rates from this, which is basically the slope of these curves on these plots, and I can do this for individual wave fields, where I just fit an exponential to the mod of the deflection, the amplitude, and then I get for each realization, of course, I get one of these coefficients qi. So what I would call the attenuation rate.
It's without water.
It's this is still without water, yes.
Still without water. And attenuation is kind of damping, no?
It's an effect by scattering, right? The system is conservative. There's no damping in the model. There's no viscosity or anything like that.
What's the reason for attenuation?
It's scattering.
Transmission coefficient.
Yeah, it's basically transmission reflection, if you
Okay.
like.
So
Yes.
transmitted, I mean, the coefficient of transmission is getting smaller, smaller, and smaller.
Base-
Because of that.
Because of backscattering, yes.
Okay.
What is how do you determine this modulus at ENI? Because you always, fluctuating. You
Yes,
sort of do
yeah,
some
that's-
tracking of the peak or something.
That's numerically quite annoying. Yeah, we do some least square fitting of curves, but the thing is, what we do is, basically that's what we're doing. Right. So if I do that for individual ones, this is what I do. How do I calculate the attenuation rate of the effective wave field? What I do is I do the exact same thing, except I average all those wave fields, as I said before. I take the attenuation rate of the mean wave field. That just gives me one number, right? For the individual ones, I get one for each realization. Here I compute the wave field, the mean wave field, and I just take the attenuation rate of that. So that would be, say, in this plot, the slope of this curve here. Okay. What I can also do, and this also applies for the problem where I put the water back in, which I'll get to in now. It won't be long anymore. I can say, well, actually, if I look at this problem, I have a two-scale problem. I have my fluctuations, which are sort of happening on a certain length scale, and the kind of regime I'm interested in is where the wave is also of that length, so it's sort of a local scale where the scattering goes on. But what I'm actually interested in is effects on a long range, right? This is exactly what you see from these pictures here, right? Whoops, sorry. The scattering goes on this sort of highly oscillatory scale, and what I'm interested in is effects over this long range. So I can do this. I can use an asymptotic analysis approach by introducing an auxiliary coordinate, say x2, which is just epsilon squared times the local coordinate. With small epsilon to get this scale difference, and I assume I can expand my deflection in this multiple scale way, and if I do that, then I can plug it into the equations and I collect terms of same order and I try to compute something, basically. So if I do that for the 0th order term, I just get the beam equation for the mean wave number. That's not very surprising. The point is the solution looks like this, and I have an oscillation on the local scale times some amplitude, which depends on the long scale. And actually, what I'm interested in is exactly this coefficient here, right? I want to know what is the large scale behavior of the thing. And then, what I now need to do now is go on, look at the first order equations, try to solve these, go to second order, and eventually hope for the best in terms of that this process ends eventually, or I can make it end. So the task really is to determine this amplitude, which determines the large scale behavior of the sort of global or sort of long scale coordinate x2. And so we can do that. One has to be slightly careful in this approach that really what can happen in these approaches always is that you get certain waves in this context that appear on a different order. So you have to be very careful that you don't do something at one order and you add it all up, and that actually accounts that it's being shifted to a different order. But we did a very careful analysis of this, and as long as the epsilon, so basically the amplitude of the roughness, is not too large, and in this non-dimensional setting, it's typically around 0.1. And I'll show that later on. This works, and it's all sort of everything stays on its order, and one can pursue this approach. And so basically, what happens is eventually what we can do is we can come up with an equation for the average of this amplitude, which of course is then which corresponds to the effective wave field. That's just sort of the price to pay. But we get an expression like this, which involves some lengthy integral, which we had to solve for numerically. But the point is, if we pursue this approach, and we want eventually we have to average in order to get something. And what we get from that is we can compute analytically, except that the integrals appear. We have to then solve typically solve not solve but compute numerically, because it's a very lengthy expression. But what we can get is this attenuation coefficient, but which then, because we've done this averaging along the way, describes the effective wave field. So for the effective wave field, we have an expression that's very simple in the sense that I can write it down on paper. The integral that you get is, you can't evaluate explicitly, but it's a very simple expression in terms of the computer can do it in no time. So I don't have to solve all these individual wave fields, average them, do that. I can pull out this coefficient very, very quickly from this expression. And then to look at some results, what do I get? Well, these are now attenuation rates, these attenuation coefficients, versus what I call the correlation length, which is basically the length of the fluctuations. And we use some basically Gaussian random processes with some where this correlation length appears. But basically, this is basically the length, the characteristic length of the correlations that we of the randomness that we've used. And what you see here, so there's three different things, right? There's the multi-scale approach, this analytic theory, which is very quick to do. I mean, it's a lot of work on paper, but once you have the expression, it basically takes no time to compute, and that's the solid line. And then the circles are the things that you get when you look at the effective wave field. So you run these 1,500 computations, you do an averaging, you pull out this attenuation coefficient, and you plot it, and this is exactly the circles you get. So spot on, right? So this is great. We're very, very happy to see that. And these two plots are again for the same kind of problem, except here it's the strength of the fluctuations is the epsilon is 10 to the minus 2, and here it's 10 to the 10 to the minus 3. Here it's 5 times 10 to the minus 2, just for two different basically strengths of random fluctuations. But what you see here also is these crosses, and the crosses are the attenuation rates that you get for individual wave fields. So what we do is we compute the wave field, we extract the attenuation rate, just as I've shown a couple of slides ago, and then for each realization we get such an attenuation rate, we average that, and this is what we plotted here, and that looks completely different, right? So basically what we've done here, the circles are the effective attenuation rate, or the attenuation coefficient, if you like, of the effective wave field. So basically, if I go back a few slides, basically the slope of this curve here.
Yeah. What's the cross?
The crosses is for each realization. This is just one realization, right? But I do that for each realization. I compute the attenuation rate of this wave field. Gives me 1,500 attenuation rates. I average those, and this is the crosses I plotted here.
Does that sort of, if you took the log of that and average it, would you get the correct answer?
Yeah, that's actually something to discuss in a second. But good point. I see I see you know a lot about this stuff. Okay, so but the point being that that these are completely different, right? And now we thought, well, this is slightly odd, so we tried a lot of other things. Like we looked at the varying mass problem, the varying rigidity problem. We came up with different with these multiple scale expansions for that. Again, they perfectly match the effective wave fields. That works very well, but not so much the individual wave fields. Yeah, we can look at maybe what's interesting as well is these plots here, where we now look at the log of the basically the attenuation rate versus the strength of the fluctuations, or the amplitude of the fluctuations. And again, you can see this is the multiple scale approach that is independent of epsilon, because I've scaled here by epsilon squared. So these are constant lines, the black ones. And then again, they match very nicely the effective wave fields, the red symbols, but not much to do with the individual ones, which are the black symbols. And again, this is for three different correlation lengths, so lengths of the characteristic length of the fluctuations. And what you can sort of see here is a tendency, if the epsilon is large, so this is 1 over 10, right? You can see already a slight deviation here. The last ones, they already sort of slide to drift off the of those curves, which is not too surprising in the sense that we've used in an asymptotic analysis. We assumed epsilon is small, so you would expect that eventually, when epsilon gets too large, and this is so as I said, this is about 1/10, 0.1. And if I make it larger than that, then basically epsilon is not small anymore, and this multiple scale approach breaks down. Okay, the other thing that is important to note is that when I draw these random realizations, I can't make the amplitudes too large either, because what happens is, so think of thickness, so I have some mean thickness, and I take some random variation of that, and my amplitude for reasonably small amplitude, so I don't know, say thickness is a meter, and the typical random fluctuation is around plus minus 10 centimeters, everything's fine, right? So typically my profile has a thickness between 90 centimeters and 110 centimeters. Now, if I increase the amplitude further, and I have a fluctuation of, say, I don't know, 60 centimeters, then things already become, so typically, then things might become slightly dodgy all of a sudden, because then some, as it is with randomness, I can have some sort of overshoots, right, in the statistics. So it might happen that I get sort of profiles where I have to subtract more than a meter from my profile, which gives me sort of a thickness which is negative, right? So this typically doesn't happen if the fluctuations are small, but once they become large, that can easily happen. And so also in that approach, I can't make this epsilon too large, right? At least as long as I use these kind of statistics. So that's sort of goes together, but still it doesn't explain why these results for the individual wavefields are completely different. And what I should say, and if you haven't realized yet, is that of course what I'm interested in is coming back to my pictures on the first slides. What I'm really interested in is what goes on in the for individual wavefields, right? Because what happens in the ocean is not some effective wavefield, but what happens is I have one realization of, say, ice flow distribution or whatever, and I want to compute. I want to know what goes on there, and not if I sort of take 1,500 marginal ice zones, I compute some strange quantity like an effective wavefield, and what goes on there. But I can do that very easily, very nicely, right? But anyway, okay. So attenuation rates predicted by this multiple scale method agree. That's also interesting to know because I can scale out the epsilon here very explicitly because I have the formula on the paper, and I get agreement between the random sampling and the multiple scale method up to about, yeah, as I said, a tenth, right? Then they sort of start to drift off. Okay, another quantity that is interesting is the phase change, and I can look at this for the effective wavefield. I ask, so what is the phase change induced by this random fluctuations in between? And I can look at that. These are the pictures here, and again for two different problems of varying mass and varying rigidity, as so phase change over correlation length, and what is interesting is that basically these curves are identical, but one is shifted by, in this non-dimensional setup, by k bar over 4, so my mean wave number over 4. And we can even show that on paper. I mean, if we use the multiple scale approach, we get explicit expressions, and which at first don't seem to be related. But if you do the computations, you can actually show on paper that the expressions are the same, except for a k bar over 4. Okay, and then what is also interesting in that sense is that because this starts at 0 and goes down, you get a negative phase change, so that actually lengthens the waves, and here, because you start at 0.25 and then go down, but not too far, you actually have a positive wave change. Okay, so so I showed you I showed you how it works for the beam in vacuum. I showed you all the results. I haven't told you yet about what happens if the beam floats on water. This will be very short because basically the results are the same. What we do here is, so we add the water, as I've already mentioned a while ago. We use potential theory. We have now a depth coordinate, which I denote by z. The plate is exactly the same as before, so we use thin elastic plate. That's actually, we neglect submergence. It's all linear theory. Basically it's an Euler-Bernoulli beam. And it has a displacement as well, where we can factor out the time dependence. So basically it's all the same, except that I add the water in using potential theory. Okay, if I do that, then of course my PDE system looks slightly nastier. I have the Laplace's equation in the domain. I have the no flux condition at the seabed. I have the beam equation as before with again, continuously varying B and G. My frequency parameter is now just slightly shifted by gravity, but otherwise it's the same thing. And I can always relate beam displacement and potential by this standard boundary condition. Now my full linear solution not only contains 4 modes, but it has depth dependence modes, and there's actually not just 4, but there's a whole bunch of them. I can set up, so the same formula, I can set up the problem as before. My local wave number now looks like this. Is the dispersion relation I get for a thin elastic beam floating. So the modes I get depend on these roots. I not only get these 4 modes as before, but I get this whole bunch, right? I get the propagating one, I get these two ones which correspond to fully complex roots of the dispersion relation, and then I get all the evanescent ones. This is also for people working with thin elastic beams floating, very familiar. Basically, all I did before, I can now do this in the same way, except that I have, instead of having 4x4 matrices, I have a lot larger matrices. Actually, they're sort of infinitely large. What, of course, I do for the numerical computation, I truncate them. So now the whole system becomes a lot larger, where this n is a truncation parameter, depending on how many modes I take in the plate. And then, of course, this looks exactly the same as before, except that there's a sum in front here now, because I have all these modes to worry about, and I have these coches, where I then have to imply the boundary, the mentioned conditions, like continuity of displacement and so on, not just in the beam, basically at one point, but through the whole depth of the water, right? So that's why it all gets a lot more complicated, but from a sort of methodological kind of point of view, it's the same thing. And the pictures I get, which is actually quite funny, I find, they look exactly the same. Again, I mean, these pictures are basically the same ones that I've shown before here now for varying mass, for varying rigidity, this for varying thickness. Again, the 3 things. The thick line is the multi-scale approach, which is a lot more technical for this problem because it's a lot more complicated, but we worked it out. And if we compare it again to the attenuation rates of the effective wave field, they're pretty much spot on. And if we look at these individual wave fields, they do something else. Okay, so that's nice from a mathematical point of view, but to see this agreement and to have done this nasty work on paper, but again, it doesn't explain why is this other curve that we're actually interested in down here. And just to remind you again, why did we do this? We want a cheap way to compute these things, right? Very sort of do as much on paper as we can, because we want to be able to compute these things very cheaply. Okay, but I've already said that. Okay, so now we wanted to really understand what goes on with this scattering. Why is the effective wave field different for the attenuation than the individual waves? And then we went back and said, well, actually, we started out with this problem because we read all these papers where people were using all these theories, using the effective wave field to make predictions about individual realizations. And we went back and looked at this, and what we realized is that almost all of these papers talk about discrete problems. So that's why here beats on a string. So basically, the simplest problem you can think of, you take a string, you sort of randomly attach masses, and you are interested in how does the wave propagate. But they're discrete scatterers, right? It's not a continuous sort of density profile that you look at, but it's discrete scatterers. And this is basically where people were very successful in applying these effective media ideas and get the correct answers for individual realizations, which is exactly what we don't get, right? Because these curves look very different. So we said, okay, now let's go back and look at these effective media theory problems. How do they work? And I'll show you. And there, for these discrete problems, I'll show you a few results as well in this context, and then I'll explain where the difference actually comes from, because then I think we've got all the stuff together to understand that. So let's look at a perturbed periodic array, in the sense that you take, if you really want to think of something simple, take the string, periodically attach point masses to the string and then randomly perturb them in position. Okay, so we have point scatterers at x equal xn. They have some scattering strength, the same one, each of them, so same point masses that you put there, and then you perturb by this epsilon times d. Okay, so that this is shifted slightly here, this is shifted from the sort of periodic position slightly there, and so on. And you do this in a uniform way. You draw from a uniform distribution, and so shift them slightly, and you do this in this way so that they can't, you can't shift this one too far over, so that it's actually on the other side. Okay, if I look at this problem like this, there's very nice theories to do that. One is by one thing that's particularly nice is by Berry and Klein, which was actually derived for in optics. For basically you take this stack of transparency slides, and because they're sort of randomly spaced, if you just put them on top of each other, they typically become opaque. And what you do is you really derive this on paper in a few lines. So you take your scatterers, they're shifted slightly by this S, and you write down, well, what happens? You have an incident wave coming in here that is reflected, some of it is transmitted to the next one, that is reflected and transmitted, but then there's a reflected wave coming in here, which is again transmitted this way, reflected the other way, and then that goes on, it's multiple scattering, right? So there's a lot of bouncing back and forth, and what you're interested in is what comes out the other end here for the T2. And if you write down what I've just said, then because you've got all this multiple scattering in between, you basically get a geometric sum. Okay, and basically, so if you sum that up, the limit is one. So if you sum up q to the power of n, you get 1 over 1 minus q, and that's exactly what I've written here. So that's that infinite sum from the infinite multiple reflections going on in between here is incorporated in this denominator. And what I do now is I do averaging, and what I do is I average, I take the square of the transmission coefficients, I take the log, and I average that. This is where the log comes in that Mike asked before. Of course, one can really discuss why should I average the log of that and not something else, but let's just do that for now. If I do that for my expression as before, I get this thing here, right? This is exactly what I had before. I square it, so there's a square here. This was already a square, so the power 4 here. Take the log, average over these over the positional changes, and then when I take the log of this quotient, I can look at two terms. The one is the log of the t to the power 4, which is what I've written down here, and actually turns out that's it. And you can show that on paper. Maybe let's just quickly maybe look at the result first, so then I can compute this. That's this. And so why is that other term disappeared? The point is, if I do this precisely, in the first step, I should have this other summand here. But it turns out by contour integration, you can show that that's actually 0. Yeah, maybe since time is going, I shouldn't dwell on this too long. But the point is that you can very easily compute this, and there's basically this multiple scattering goes away. If I average, and that's the key point to make, overall distances, so they have to be far apart, and the randomness has to allow for all the phases to be included. And I can do this for n scatterers, basically this argument, and then I get this thing here. So basically, this attenuation rate is just basically the log of the transmission coefficient of one single scatterer. What I have to be careful though is that I have to have this this randomness has to be large enough, otherwise this averaging wouldn't have been allowed. Okay, so in particular, this implies that I have some constraint on the distance and the wavelength. If I don't do any phase averaging, I just get individual wave fields. And the point is that this computation on paper is very, very just made for this specific thing. I can be a bit smarter in the sense that if the problem becomes more complicated, I can do the following. One thing that people like to do is this potential approximation, where basically what I say is I have this random medium. Otherwise, the problem is the same here. Again, those point masses, think of them as point masses on a string. And what you do is you say that there's a following argument. You say, out here there's an effective wave number, out here there's an effective wave number as well, and then you look at one cell and you do a random perturbation in here, and you say, well, actually, if this is just any cell in the random background medium, what should happen is that the average reflection is 0 and the average transmission is 1, right? Because you've just picked that out and you shouldn't see it, right? And you can and the average again here is this average over the whole distances. And if you apply these two conditions, you can actually derive an attenuation rate. I don't want to go through all the details, but that's basically the idea. And this is well known as well. So there's some very nice paper by Agnes Morel, Paul Martin, and Vincent Pagneux, who've done this, who've used this idea to derive analytic expressions for these effective wave numbers for small epsilon. And Luke and I have done some work on that as well, which actually is not even, it doesn't need the epsilon the epsilon doesn't need to be small, but the drawback is then that you need to do some numerical minimization. That all works fine. You can even extend it to multiple directions if you have a 2D problem in that. So the CPA is also very, very mighty in a sense. And you can look at the results. So what happens? Well, if you here now look at this attenuation rate over scattering strength, sorry, this time it's not scattering strength, but distance of fluctuations. You see that the individual ones, they match nicely with the CPA approach. If the scattering strength is, sorry, not the scattering strength, the variations are large enough, then you obtain this what I call the very inclined limit, which I can really derive on paper without any more doing, which needs that the epsilon is large, so it makes sense that eventually they only approach here. So again, this works very well. What I want you to realize, though, is the pluses here are the individual ones, and this is my averaging method that I used, right? So here, the red things lie precisely on top of the other ones. So here, this whole idea works perfectly well of taking the effective wave field, effective media theory, to come up with what goes on for individual waves, right? So this is actually sort of going a bit further. This is actually why we thought we can use this idea for our continuous beam problem. Okay, so the effective field predicts the individual ones, great, in this discrete setting, but we've already seen, at least for those continuous problems, it didn't work. And the question is why, and I'll explain that to you in a few seconds, and maybe to give it away a little bit. If you think about it, if you step back and think about it, it's not so unobvious, but it's still interesting to see how quickly it happens. Okay, so what did we do? We said, okay, then now we need to relate these two problems. And so we said, well, we must map the continuous onto the discrete problem and learn what goes wrong, basically, what happens. And so let's stick with the string problem for a while to keep things very, very simple. So the continuous string problem looks like this, right? I have some random wave number variation. Again, in the same setup as before, I say the wave number varies in a random way about the mean wave number k bar. I have some strength nu here, and the beta again is a random process of order 1 and mean 0, exactly the same as before. Then I can write my variation for one realization as before. I can even take a step approximation. That's what you see here. And what now I need to I map this to a discrete problem, right? This is my continuous profile. So what do? I identify these what I call humps. So basically, I take two minima of the profile, and I say, well, this I take as one scatter. And then I do this. I go to the next minimum. That's here. This is one scatter, and so on. Right? And I use these. I take these humps for each realization of the profile. I compute all these humps. I compute their scattering strength, and I compute a basically sort of an average scattering strength in that way. So in that way, I map the this nu here to the scattering strength. If you think of the beats on a string again, because I have all these beats which are of the same scattering strength. Okay, I can do that. The first thing I realize is that actually what's very important to note, and I know that this is an important point from this very inclined limit, where I know I have to include all phase changes. That if depending on how rough the profile is, now this is the correlation length here again, which remember one was where the profile was very rough, these are more smooth variations, I get very different histograms of phase changes. So the phase change seems to be a big difference, but what I can see is that this correlation length, so the smoothness of the radiation, the characteristic scale of the roughness, is actually related to the epsilon before. And what I also see, I don't really get a uniform distribution. I get these different distributions. Okay, so let's look at some pictures if I do that. So I have my continuous profile, I have my discrete approximation by these humps, and now the crosses are the continuous one, the diamonds are the discrete approximation, and these are again attenuation rates over the strength. And what you see here is, this is for different correlation length, and you see, well, usually they match quite well, but what happens here, they tend to drift off if this eta gets too large. And what you also see is that this seems to happen earlier, the larger this correlation length is, so the smoother the oscillation, the smoother the profiles. So the discrete approximation generally works, right? This hump regime, this hump approximation. So if these agree, there must be some regime where the effective waves are where the attenuation rates of the effective and the individual waves agree. And so one can look at this problem, at this thing here, where we look at the again the attenuation rate where the scattering strength, and this is for 3 different epsilons now. Which you can think of as the correlation length. And what you see here is, again, these 2 curves, they nicely, the circles and the crosses, they all tend to agree as long as I'm out here to the right. And funny things happen on the left when the scattering strength is small. And in particular, these are the effective ones, yes. And they sort of overshoot. So that means that there's actually stronger attenuation than the individual ones would show, which is exactly what we found for the beam. And okay, so here's the answer basically. What happens is the following. So this is the plot to look at. The attenuation rate versus the scattering strength. And basically what we see is the circles and the crosses, they don't agree for quite a long time. And then all of a sudden they come together. And we see, this is for short correlation length, so it's quite strong scattering. These are for smoother oscillations. And again, the same thing happens here. Scattering, when the scattering strength is small, they don't agree. Then all of a sudden they quickly come together and they stay together. And the dotted line here is the multiscale method, where you can also see that actually basically the deviation of the effective wave field attenuation rate from what the multiscale method gives starts to deviate exactly in that moment where these 2 tend to come together in this very small region of change. And this, yeah, as I said, this is a plot for a large, for where the wavelength is of the same order as the characteristic length of the fluctuations, and this is for a small regime. But the same thing happens. So basically, if to come back to the question we had before, the point being that if we make the effective wave, if we make the scattering strength large enough, these come together and the multiscale method breaks down. So now you may ask, why didn't we notice this before? This is actually quite obvious now that you think about it, is that you just need strong scattering. So if the scattering is too little, then you don't get this, then for individual waves, they're just not attenuated enough, and nothing happens. Well, point being is that precisely this region nu leads to unphysical values. That's exactly the point, or sort of the start of the problem, where if you look at the problem and you think of thickness, you get a lot of these overshoots where you get negative thicknesses. So actually what we had to do to obtain these plots here on the right-hand side, basically past this line here, is to apply a numerical cutoff scheme. And basically cutting off our realizations, basically saying, well, if I start with a meter thickness, and all of a sudden I want to basically prescribe a minimum thickness, say it can't be thinner than 10 centimeters, say, which of course screws up the statistics of the randomness profile, but actually not by much. That's something we found. That's actually something that one could investigate in more detail. But the point being is we never got these before because we always said, well, we can't go past the thing where you regularly get points that have become unphysical, right? And only after all this theory that we looked at, we said, well, we have to go into like basically from these plots here, we have to go into deeper and increase the scattering strength to get a regime change, and that's actually exactly what we got. Okay, now I think I've just want to show you these plots as well, where you can now nicely see again effective wave fields versus individual wave fields, and you can see that for small strength, the attenuation of these is a lot larger, and then they sort of tend to come together. And for 0.2, which is sort of roughly somewhere here, where they're just coming together, you can see that nicely matches. Okay, I think I've actually talked a few minutes longer than I anticipated. So just very quickly, the key findings is that there's really the scattering strength that controls whether the attenuation of the effective wave field approximates individual wave fields. If you want all these, use this multiple scale method, effective media theory, all the stuff that you can nicely do on paper, you only get decent answers for individual realizations when there's a lot of scattering, let's put it that way. And what is interesting is that this transition is very rapid, right? The curves are very, the plots in the previous slide, they're all very straight, and then they come together very quickly. So the question is, I mean, this would be interesting to investigate, but what we're really interested in also is because most of those methods that I showed you always rely on approximating this Q effective on paper when the scattering strength is small. So can these theories be extended to a larger scattering strength regime? And of course, most of what I showed you was 1D. This comes back to Mike's question. Can we extend that to 2D or 3D? And actually, the last question, which I didn't put on the slides here, as I've just noticed, is that now that we've learned all this, of course, what we want to look at is how relevant is this effective media theory for wave propagation in the ocean. And my guess at the moment is that probably we can use that only in very particular situations because the scattering has to be very strong. So if you just have, I don't know, if you're far out, if you're in the marginal ice zone close to the ocean edge, then scattering is so little that basically this effective media theory probably won't give any useful answers. Thank you very much.
Yeah, I've got lots of impressions, but I think you can apply this theory to lots of different problems as well, though, right? It's not limited to...
Yeah, this is where we started out with, but yeah, no, definitely. I mean, particularly because this was also our intention to, on the one hand, to understand this in a deeper way, but also by looking at these problems. I think the effects we found and these transitions of regime and that sort of stuff, because they're so genuine, I think that is actually basically true for a lot of problems involving scattering, say, in a very broad sense.
Referring to your very last comment, where scattering may not apply to, where we are close to the ice edge.
No, scattering does apply, but it's too weak for effective wave fields to be
It's weak for long waves, but it's maybe strong
for high frequency. Yeah.
Yes.
Not true. Yeah, that's true. Yeah.
Yeah.
But those are exactly those things that we should probably go back now and think about a little more. Where these exactly, I mean, how narrow this regime, or what are the particular cases where this might be interesting.
Okay.
But no, that's a good point.
Then it's also, I think, important because when you add the water below, then you have these other modes that are probably also scattering energy at different frequencies, which may scatter strongly as well, because their wave number is increasing. It's different compared to scatterers.
But you're thinking of including more modes of different frequency now, or?
Yeah. Not in the potential flow theory, but in nonlinear scattering.
Okay,
Let's
right.
say
If you shift energy to different modes, then their scattering might be stronger.
Yeah.
Okay, that's an interesting point. Okay. Yeah.
I'm looking for the applicability to the marginalized zone.
Okay. Fair
and
point.
it seems that finally strong scattering is well modeled by the discrete model.
Yes, that's true. Yes.
Okay.
That's definitely also what is quite interesting, to see.
It seems the problem as it's presented, it's more about scattering and propagation in optic fibers than in ice. Because it's one-dimensional, right?
Yeah.
And,
Well, I have
it's the same, yeah. You change properties of that somewhere, and but it's more localized. It's not like a continuous inhomogeneity, but
the paper I referred to somewhere in between where we did where this CPA approach, coherent potential approximation approach, works quite well even for multiple angles and that sort of stuff. That was actually a 2D theory, and there we basically what we did is we took line arrays and we added line arrays onto basically one beside the other for very many of them, and we started randomizing that, and that's why also you get the different directions, because all of a sudden then of course you can have waves traveling in different directions, and for that that was of course a discrete type of discrete setting again, but 2D, so in the plane basically, and there we also found that this coherent potential approximation in this discrete setting approximates everything very well. So we've already worked on generalizing this a bit, but my guess is from what we know so far is that I mean in 1D if we find that we need strong scattering, and then if we have more directions and more more things that we tend from a general tendency, scattering is not as strong in these cases, right? So if in 1D we see it doesn't quite work, I think at least I would be careful, but of course a lot of other things go on. But point I want to make maybe is just that we've already extended that to sort of 2D kind of situations, and the general ideas can be applied.
Just to the change of the thickness, for example, along your direction of propagation. It's not like you use no restriction on that, so it's not necessary. It can be any, right?
Well, what we do for the simulations is we basically what we want is a Gaussian random process and we prescribe a correlation function like an exponential. So and how do we realize that numerically? We basically take a sum of cosines, so they're automatically smooth. And so in theory, you have to take an infinite sum of cosines with random amplitudes and random phase changes. But of course, we truncate that at, I think 100 or something, I have to look it up. But we truncate that sum, but because we sum over cosines, of course, our profile is always automatically smooth. Okay. But you could shape something else.
Yeah, but if I formulate the question, the scale of these inhomogeneities and length scale, how they are related? Is it any relation between them, or?
Well, we have the strength, which I denoted by epsilon. We have this length scale, which is the lowercase l, which because I take these Gaussian processes, so it's basically correlation length.
Yeah.
And you can vary these.
So it's any.
It's any. Yeah.
Okay. Yeah. Okay. So the actually kind of realization of your thickness is can be any.
Basically, but you have to be careful because, as I said, once you get sort of negative thicknesses, it becomes unphysical. Then you have to be very careful. And the way, as I said, the way we solved this problem was we basically used numerical cutoff. We said, well, if our medium thickness is, our mean thickness is 1 meter, then if we get if we're told that we should subtract from that more than 90 centimeters, then we just cut it off at 90 and say we never go below 10, right? And of course that changes the statistics though.
Yeah. If we say it's I'm not sure, but it looks like a uniform distribution. If we say that at any point thickness can be any from 0 to say 5 meters. So not Gaussian, any from 0 to say 1 meter.
But then you basically you don't have a length scale anymore, right?
No, nothing.
then you have nothing.
Yeah,
you,
yeah,
basically
yeah.
have you basically have white noise, right?
Why not? White noise.
But you can-
I
you can-
believe you mentioned white
No,
noise.
I haven't mentioned it, but you can get a kind of white noise if you let the correlation length go to 0, because then you basically are correlating.
Okay.
There's in lots of my
Okay.
plots, it's the far left end of the
Yeah.
theory. So it's
Yeah.
basically the homogenization limit. If
Yeah,
you
yeah,
like.
yeah, yeah. From that point of view, there is that Q effective and Q individual. Which of them is important from practical point of view?
Well, in the plots I show you, one has to be slightly careful, but in the plots I show you, it's
No, in reality.
in reality.
Well, yeah, not in the plot.
Okay. Well, the point. Okay, now
Reality hasn't come anywhere near this,
the point is that if you have white noise, then you have that's basically the limit where your scatters are very, very small or short, if you like, compared to the wavelength, right? So I think then there's a lot of situations where that applies, but I think in the marginal isol setting, where you have the wavelength being roughly the same size as the scatters, you're never in that limit, right? Because basically it's a small scatter or long wave limit that you look at.
but you to be careful here because, you've got everything. Eventually at some point the waves are, we've said that it's not scattering that's causing it in that limit, but we don't know. It's worth investigating. Worth trying to work out of it. I think that, nobody knows. Like maybe the long scattering limit at least,
Okay.
why wouldn't the scattering, when it becomes weak, the attenuation is weak anyway, so.
But typically, if you really go into the limit, what happens is that the waves propagate, and you just get an effective wave number, right? Which with some phase change, say.
Yeah.
So basically, just sort of physically speaking, if you have a very long wave, you have a small scatter, you don't get the wave doesn't really see
But
any.
I think, I'm not saying that, I'm saying it is important, but I think stating clearly whether it is or it isn't is important.
Mhm.
If you say to me, I've proven it doesn't matter, or more evidence that it doesn't, that's great as well.
Yeah,
Because
yeah.
we don't know, we don't really.
Yeah. No, we need to look
compute that
more into
limit.
but my hope was or our hope was exactly to look into these things more closely and to understand that better. Right, to say basically if you do this, then this is the result. Does that actually in any way fit to what we know, what we see, what goes on or not?
But could you return to the slide with that B of X and G of X? It's a very big image.
Quite at the beginning.
Yeah, Okay, so so this equation you solve in interval, right? The two discrete. So if we say B of X is in certain interval, right? And G of X in certain interval, and we now only that ends of that interval. That's all, right?
Okay.
And we know the incident rate. Can you estimate the transmission and reflection coefficient in terms of the intervals?
Well, I mean, the question is how is the B and G distributed, right? You mean
No, just intervals. We do not know. How they distribute, because the problem is nonlinear, right?
Okay.
So the say V is from 1 to 2, any. And G of X is from 5 to 10, any.
Okay.
And we know the incident wave amplitude 1, linear problem, right? And then we need to estimate the reflection and transmission coefficient. Is it possible to think?
I would
Because
think
if we solve this problem, then we...
my hope would be for this reasonably simple problem, as long as it's
Yeah,
a linear problem,
yeah.
you can sort of use. I mean, this is an elliptic problem, right? So the question is, if you look at results like continuous dependence on the parameters,
Yes.
and usually you get something.
Yes.
I mean, there's typically some constants appearing that you don't know too well, like some.
Exactly.
But otherwise, I would think that you can at least. I mean, you can get something. The question is how sharp these bounds are. Right? I'm sure you can obtain something.
Yeah. But
Which
also,
probably depends on the, say, H2 norm of the B and the L
but
norm
also
of
it's good.
the G or
It's,
something.
you can start from that equation directly, but then the result could be not practical.
Yeah,
right?
yeah.
But if you behave in smarter way, then it's possible to do something more reasonable, I believe.
Possibly, yes.
Possibly.
But you assume that B and G are constant in those small intervals? Is
In the step approximation,
step
that's exactly what we do,
approximation.
yes.
Yeah. So this is how you get the wave number, I suppose.
This is how we get the very local wave number, yes. So basically, for the numerical, not for those other approaches I showed you, the more sort of analytical
Right.
approaches, but for the numerical approach, we discretize exactly in this way where we get the step approximation. So we
Yeah.
have these steps, and in each of these steps, it's constant.
Yeah, I see.
yes.
Yeah, okay. But do you assume that also to get the local wave number? I mean, you have to, right?
Yes, yeah, you
Yeah.
get a local wave number.
But
Yes.
it's the same.
But you can compute it, right? It's
Because
it's
without
something.
water, it's yeah.
Yeah, but I mean, in principle, I mean, if you take the Fourier transform, I mean, you get a convolution, right? I mean, between.
Yeah,
B-
you can.
But then you don't get this k of x, right? I mean, it's more complicated.
But then you discretize it.
But yeah,
You
I
have
mean,
the same.
you can use it. We looked into that at some stage, and
Yeah.
and you can do things along the line along those lines. But then we thought it's much simpler to look at it this way.
Yeah. This is the question, are you discretizing at the beginning
Or
or
at the end.
At the end, yeah.
Right. Right.
Kind of that.
But there's actually what you're saying is actually, well, it's to some degree similar to this validation approach I showed with
Oh, the
these
Green's
equations.
function. Yeah, right. Yeah,
Yeah,
right.
Thank you, Malte, very much. Thank you.